Okay, so for this first one, is it metric or standard? It says inches, right? So hopefully it's standard, right? So 2.515 inches. Good. How about this one? 2.3, 2 whole inches, 0.3, and then 65. So 2.365 inches. Any questions on those first two? You got it figured out?
Yeah,
Decimal. Okay. Now for this one, standard or metric? Inch again, right? So, oops, get out of it. Stop doing that. So anyway, let's do the first one while I'm waiting for my computer to correct itself here. There we go. The first one, is that 6 point or 0.6 or what is it?
0.6.
It is 0.6. 25, right? Come on now. It is past the quarter mark, so it is 0.625. Wow. It's going to be one of those days, I'm thinking. Well, it's because I'm trying to write over the top of inlaid images. So let's switch this order now. Okay, there we go. We'll get back where you're supposed to be. So there's 0.625. I'm just going to put it over here. 0.625. That's for this one, of course. And then what else? 1. So it's 1,000. So that's 0.626 that reads, correct? How about for this one? 0.875 plus 0.023. So 0.898 inches. Okay. Any questions on those two? 0.626. This is 0.6 here. And then that's 0.625 to there. Then plus another 1,000. Try these 4 quick. Let's go through them. I realize they're kind of small. So this one up here is 21.05. There we go. This one here, 10, 11, 12, 13, 14. 0.03, good. Not past the half mark, so you don't have to worry about those, and neither of those. Make these a little bit easier to read. So this one is it past the 9? Just past 0, so that means it did pass the 9. 9.12, that is in millimeters. And this one, that's 6567.47. What do you think? Doable? Okay, well then we are going to pause for a quiz. Alright, so today our first thing we're going to talk about kind of ties in with the stuff from measurement. But we're going to look at kind of a blueprint reading application. So let's say you have an object like that, and it is labeled 1.500 inches. Now, first of all, are those zeros important? Well, numerically they're not, but because of the measurement, those zeros are telling us that that's not just measured to the 1/10 of an inch, it's measured to 1,000th of an inch. What's that saying? Plus or minus 6 thousandths. Now, a lot of people call it a tolerance. The technical name for it is an allowance. A tolerance is slightly different. It's part of a tolerance. It's slightly different. So what that is saying is I want this in an ideal world. This is my desired value, or sometimes called the ideal value. In an ideal world, I would want to make this exactly 1.500 inches every time. But I know the world isn't perfect. So I can be off by as much as 6 thousandths either side. So what it is creating is a range, just like we had with our other measurements. The range is the 1.50 minus the 0.006, or 1.494 inches, to 1.500 plus the 0.006, or 1.506 inches. Simple enough? Okay. Another way of writing it would look like this. What's that saying? 0.4% of the measurement, right? Plus or minus 0.4%. So to figure out what the allowance, oh, by the way, you said tolerance. This is the tolerance. If I subtract that, I get a range of 0.012 inches. That is my tolerance. A lot of people call this the tolerance, and I mean, I wouldn't mark it wrong if you called it, but technically it's called an allowance. So anyway, here we can calculate the allowance. It's 0.4%, so it's 0.4 over 100. And how much is that out of 0.850? So 0.4 times 0.850 divided by 100. So 0.0034. So what this is really saying is plus or minus 0.0034 inches. Usually about 0.5% to 1% is what your allowance would be if it's done like this. This is what we call a relative tolerance or relative allowance, however you want to put it. Where the size of the allowance, the size of the tolerance, which is double the allowance, is just determined by the size of the measurement itself. What we had up here, this is called an absolute allowance or tolerance. Same words we used before for our errors, absolute error and relative error. Absolute error was just the difference between the measurements. The relative error was the percent difference. Does that make sense? You suppose? If it must. That's the object that I'm dimensioning. This right now is an absolute tolerance, given as with an absolute allowance. I want you in your notes to convert that to a relative allowance for me. So we're going to set this up as blank over 100 because we're changing it into a percent, equals 0.010 over 2.500. Cross multiply and divide, we do get 0.4 over 100. So it's plus or minus 0.4%. How many of you had that? Okay. Didn't even get close. What did you do wrong? Didn't try? Oh, gotcha. What's this saying?
That means you can't go positive.
Yeah, it's still saying my desired value. In an ideal world, I want to make all these exactly 0.800 inches, 800,000ths of an inch. But since the world isn't perfect, we can be a little smaller, but we can't be any larger.
How would you write that as a fraction?
Is it a percent? You can't. Well, you could put it. You would put it as a plus 0% or minus whatever percent. It would actually be point. Oh, what is it? It's like 0.125% or something like that. Or 1.25% technically. But yeah, you'd have to have separate percents. You couldn't do it as one. So here's the question. What's the implied range here? It's 0.800 minus 0.010. So that's 0.790 to 0.800 plus 0.00. In other words, 0.800. That's my implied range. Now, one of the things we're going to work on is, given the implied range, this is what we call a unilateral tolerance. It only goes in one direction. The ones we've been working on up here are what we call bilateral. There's an allowance in each direction. But if we assume that it's bilateral and we're given the range, how would we find our ideal value and our allowance? Well, the ideal value, if we assume that this is bilateral again, would be directly between those two numbers, wouldn't it? How do we find the amount that's directly between those two? You average them together. Add them together and divide by 2. That would give us 0.795 inches. So that would be the center of that range. That would be our ideal value if this were a bilateral tolerance. How do we find the allowance? Our allowance, we take the difference of them and divide by 2. That would be 0.005 inches. So what this is saying is that range would give us a bilateral tolerance of 0.795 inches plus or minus 0.005 inches. Do you see where I got that? So here's my question for you. Why do I write it like this instead of like this? Well, because I really do want that 0.800 inches. I don't want 0.795 inches. And when you go to manufacture it, the machine you're using to produce this, to fabricate this, has some sort of capability. Let's say the machine you're using is capable of producing the plus or minus 0.003 of an inch, right? And you're thinking, well, yeah, geez, I could just shoot for 795 thousandths and I'd definitely be within my range. And you're right, you would be. But do we really want them to be close to 795? Oh, we'd rather have them close to the 800 thousandths. So if I know that my machine is capable of producing parts within 3 thousandths of where I set it, if I had this listed, I would still set it at 0.795 and it would just go from 0.792 to 0.798. Does that make sense? But since I really want it to be this, what would I set it for if I was shooting for this? I wouldn't set it for 0.800 because I can't go over. I'd probably set it for 0.797. So even if I am 3 large, I'm still at the 0.8. I'm not over my range. Does that make sense? Mm-hmm. So this is telling us, depending on the capability of your machine, you want to be in this range, but depending on the capability of the machine, we want to be closer to the upper end if we can. So given this allowance here, In your notes, create the range for me. Okay, so what's the lower end of my range? Sure, 1.850 minus the 0.008 is 1.842. Up to? Perfect. 1.850 plus the 0.008 is 1.858. Let's go the other way. In your notes, if I give you a range of 0.796 inches to 0.808 inches, find the ideal value and the allowance for me. How do we find the ideal value?
Add the first one to the other one and divide by 2.
We add them together and divide by 2. Gives us 0.802. How do we find the allowance? We subtract them and divide by 2. Plus or minus 0.006, correct? So this is 0.802 inches plus or minus 0.006 inches. Once you found this, subtract one of the other two from it. That works as well. Yep. You get the same answer. There's something called a clearance fit. What a clearance fit is when you have two parts that have to mesh together and not bind. There are several examples for this, like in a door. The bolt in the door, it has to fit inside that hole, but it has to be able to slide in and out without binding. So they don't make that bolt the same size as the hole or it would bind. So there's some clearance there. If we're looking at doing like engines, if you have some larger engines like starters and alternators and stuff, the heavier ones, they actually have a locator pin on the block where there's a hole in the starter or the alternator, and you just slide it around until it slips over that pin and it holds it in place when you get the bolt started. Same type of thing. It's got to be able to slide in and out easily or it doesn't really serve much of a purpose. So let's look at this. Let's assume this is a bolt going sliding in and out through a door. Let's say that this is 0.620 inches plus or minus 0.005 inches. And this over here, let's say that this is 0.635 inches plus or minus 0.005 inches. It's what we call a clearance fit. There has to be extra space. So what I want to look at is I want to look at the bolt and the hole, and I want to describe them a little bit. I want to find the smallest size and the largest size, the minimum and the maximum. For the bolt, what is the minimum size it can be? 0.615. What is the maximum size it can be? 0.625. Subtracting the allowance and adding the allowance. For the hole, what is the minimum size? 0.630. Maximum size? 0.640. So now we're going to talk about clearance. The minimum clearance comes when the bolt is large and the hole is small. How much clearance is that? 5 thousandths is the only difference between them. A couple specks of dust might bind that up. Now, if you get any sort of grease or rust or anything like that on there, it is going to bind. Maximum clearance is when the bolt is small and the hole is large. How much do we have there? 25 thousandths. or a 40th of an inch. That's probably not too bad. It's not getting real loose, but if it was something more precise, you wouldn't want it getting that loose. You can see that it's the buildup of those tolerances that can get really cause a really big range there, because if they're both on the right end of the range, we can have a big difference between their sizes when they mesh together. Tolerance stacking, tolerance buildup. Technically, tolerance stacking is, let's say I have a part that has several features. Each one has a tolerance. Let's say this is 1.200 inches, plus or minus, whatever. Let's say all of them are at the plus side of their tolerance. Well, then to get the whole dimension here can be off by like half an inch. If they all have a 5 thousandths tolerance, you can be 5, 10, 15, 20, 30 thousandths large just on those few features. So that's why the accepted in mechanical design now, instead of, and it used to be you dimension each feature like that. And then if they all are on the same end of their tolerance, they could be the whole dimension could be really large or really small. Now they use what they call a dacum. A dacum is just a reference line. So everything is referenced off a dacum. So this would be the dacum for this is the bottom. And so you dimension this from here. Then from here you dimension up to there. From here you dimension up to there. Everything's dimensioned up from there. So each location has its own tolerance, and it can't possibly build up on other tolerances. So whenever possible, that's the standard now, is to try to don't dimension something off of something else that has a tolerance on it. Yeah, because the most any of these features can be off is by its own tolerance, not by a buildup of all the other tolerances. There's also something called interference. Anybody here ever put a frost plug in a car? A frost plug is actually pressed into the block of a car. And so if it builds up pressure, it pops out. So if you get if it freezes, if you don't have enough antifreeze in there or whatever, so any of the fluids freeze, that'll pop out and save the block from cracking. Now, if it still freezes hard, it's still going to crack the block. But it's a safety measure is what it is.
I thought they had to put them because when they use the sand or whatever, they have to get it out of there when they use it again. So it's not actually made for that.
Yeah. Well, no, it's when they mold the blocks. They actually use it's foundry sand that they use to mold the blocks. That is one of the things. But there's a lot of other cavities that they can get them out of. But yeah, that is one of the reasons for it being there. Yeah. So they tighten down. Yep. Those actually don't pop out easy enough though. Yep. They do. Actually, one of the biggest issues with frost plugs for quite a long time was rusting out. I think now they've switched to aluminum, but when they were still steel, they would rust out, and you'd get radiator leaks. You'd run your radiator dry. Well, you can actually run an engine quite a while without cooling it. It's yeah. Well, I mean, it really does not hurt an engine unless you really work it hard. It's the oil, running without oil will destroy it. Yeah, if you don't move. Okay, so let's say that our plug here is dimensioned 0.810 inches plus or minus 0.005 inches again. And our hole here, 0.800 inches plus or minus 0.005 inches. So again, we're going to look at our plug and our hole. What is the minimum size of our plug? 805. What is the maximum size of our plug? 815. For our hole, what is the minimum size of the hole? 795 maximum? 805. Now, interference is the amount that the interior object is larger than the exterior object. So in this case, the plug should be larger than the hole. The minimum interference is when the plug is small and the hole is large. What's the minimum interference here? 0. There is no interference. Now, it's still going to probably stay in there because there's going to be dirt or whatever that's going to hold it in place, but it's not going to take much force. That engine just heating up is probably going to pop it out. Our maximum interference is when the plug is large and the hole is small. What's that going to end up being? 20 thousandths. That's probably about right. Might be a little bit of a tight fit, but it's about right. One of the issues, when you hear about aftermarket parts, how aftermarket parts are designed, I mean, your genuine dealer parts, they come off, they're more expensive, but it's because the design, they come right off of the design, the drawings for that car, where that part is actually designed out. Aftermarket, what they do is they'll buy a couple dozen of the genuine dealer parts, and they'll measure them, and they'll engineer them off those measurements. So they'll take all those, they'll measure them, average together the measurements, and okay, so this is what we're going to produce. Well, if they happen to get some that are on the large end, they're going to be producing parts that are just a little bit large. And so they're within tolerance in most cases, unless they get to one far end of that tolerance, then they're not going to fit real well. So that's why aftermarket parts, they say, don't work as well. It's because they're not working off the blueprint. Now, chances are, if they're taking, like I said, a couple dozen, 20 or 25 parts, they might get some that are a little on the small end, but they're going to get some a little on the large end. They should average out to be really close to the design size, but it's always possible that they can get a bad, that they just take a sample that's all too small or all too large. So it is very possible they can do that. It's an art to do it. It's very statistical. But anyway, there is always that risk with the aftermarket parts that they did get that. I mean, you're talking about the way they do it is they call it a 95% confidence. So about 5% of the time, or 1 in every 20 parts, they will have that bad batch where they get a mean that's outside of the acceptable range. So it's 5% is a pretty high percent when you're looking at that. But so there is that risk. Okay, in your book, page 198, exercise 4.7. We're looking at 1 through 41, the odds. I'll give you guys the next 7-8 minutes or so to work on those. We'll take a break, and then we'll lecture our second half of the class.